decimals. Like
So you scoot the decimal the
just
same
like you
amount.
would do it. Okay. That's all I did.
Oh, okay.
That's all I
But I'm glad you asked this one, because I think last week, Friday, somebody asked one and they went some of the way, but not all of the way. So now we actually did one. Okay, another question.
Number 10, the fraction.
Number
Last lesson.
10 on the fractions. Okay. So turn-in problems, not shape-shifting, but here. Ah, yes. Every term people want this one.
did.
Okay, so our first thing we are asking is, what is 2/3 of 7/8? Does that make sense? That's our first question. And then we're going to ask, what is 1/4 of, and whatever we get as an answer for part A. Any questions about why those are the two things we're asking? Okay, what do I change of to when I'm making word problems into equations? Times, yeah, of is times. Should I multiply across top and bottom? Should I be tricky and do some canceling first? Let's do some canceling. So divide by 2, 7 and the 3 have nothing in common. So that's 7/12 of a pound. And again, of means times. No canceling this time. There's a 4 and a 12, but they're both on the bottom. So I can't cancel things unless one is top and one is bottom. Questions about that one now that it's up on the board?
Yeah. So it's not taking 2/3 away from the 7/8?
No,
It's not subtracting?
no. 2/3 of means that she had this bar that weighed 7/8 of a pound. She must have had someone else in her will. So she chopped the bar into 3 pieces and Lloyd got 2 of them. So of is multiplied. You get 2/3 of something, we're not subtracting it away. We're making 3 pieces and you get 2 of them. It's similar to if we had a sheet cake and there was this much left of the sheet cake and we said, you get 2/3 of it. Then we take however much is there, chop it into 3, and you get 2 of those. We're not subtracting 2/3 away. Does that help? Sure, yeah.
I'm just seeing like she has 7/8 a pound bar. And then just that they're giving her 2/3.
If it said 2/3 of a pound, that might make sense. If there was a word right here that said, she gave him 2/3 of a pound from this much, then that might make sense, but that's not what it says. Would it be less confusing if the 2/3 is written out as TWO dash TRI? No. Okay, other homework questions. Number 9. I'll set it up, but I don't want to do it for you all the way, because it is a turn-in problem. So actually, I'll just change the numbers, then we can do it. Okay, so I'll change the numbers and then we can do it, and I won't give away the answer. So we have 2 1/5 yards long, and anytime we have a mixed number, we don't like that. We're going to make it, oops, I don't need an R in there. We're going to make it a improper fraction. So 2 times 5 is 10, plus 1 is 11. And then we take that amount and we want to make 4 pieces out of it. So what's my next step going to be? What's arithmetic for cut it into 4 pieces? Yeah, divide by 4. Oops, come on. It's not letting me write. Okay. Okay, how do I take a fraction and divide it by a whole number?
You just have to turn the whole number into a fraction.
Yeah, so it's 4 over 1.
And then you have to flip it and turn it 11/5 times 1/4.
1/4. No canceling, so 11 20ths. We're in yards. So your numbers will be different with the actual one, but these are the steps. First, we're going to say mixed numbers are ugly. I want an improper fraction. And then you're going to divide it by however many pieces it is. 7, real 12. You can be done. You have another question?
I need help with percent and decimal. Even
Percent?
though I do know what to do, I feel like I'm still not getting them right.
Which one?
I feel like I'm doing the exact same thing, but I'm not right. Unless I am getting them, I just. I don't know. Can we just?
Okay, check with one of your neighbors before we go.
I know, right?
At least the ones I'm glancing at look okay.
Why do I feel like I've done this assignment twice and I've gone over the homework in it and I'm getting it right? I don't.
I don't know. Show me and I can know more, but not during class if you're not ready to just ask a question. Okay, so we ended on fraction, addition, and subtraction. There were 3 different ways to do things, and one of them was just hard to explain, so I'm going to try again. To summarize, actually, let me start just by, we started by summarizing last time, so let's just look at that. Okay, so there were 3 different cases of adding fractions. The first 2 were kind of straightforward. If I could change one denominator into the other, then that makes sense. If I can't change one into the other, and they have no factors in common, then I'm stuck. I have to brute force it, multiply each denominator by the other, then they'll be the same. Whatever 10 times 3 is, even if I don't know it's 30, it's going to be the same as 3 times 10. So multiplying each denominator by the other always works. To be fair, I have to do it with the numerators also. The problem is I may just get a big bunch of stuff that's annoying. The third case was that there is something in common, the two in this case, and I don't want to do this brute force method. I'll multiply each one by the other because I'm getting bigger numbers than I need to. 12 could have worked just fine in this case. So what do we do in this third case when there are some factors in common and I want something smaller than just multiplying each denominator by the other? Okay, everyone with me is sort of where we are.
So, to get the, you would have times them, to get that, you were times you by two, get what you got, right?
I was doing this one sort of the inefficient way. By multiplying each by the other, I can always add them, because I will always get the same number on both,
Okay,
but it's bigger than it used to be.
oh,
There's a better way to do this that's more efficient.
this one,
So let's look at it with slightly bigger numbers. Okay, here.
I don't know if you have read it. There's some wrong. You don't know which ones.
Actually, let's just do all of these.
Yeah, did. I did.
Let's make sure you are following me so I don't trust you too much. Which case is this one?
I know how to. They have some things in common.
Wait, what?
This is the case.
You only have to multiply the 1/6 by 6.
Yeah, this is that first case. I can change one into the other one. I don't have to mess with them both. Whoops, that's not a 1.
Oh,
Everyone happy with that?
because 6 goes into.
36.
6 goes into 36.
All right,
You don't go across.
yeah,
You don't-
yeah, I get that. So we gotta change
Okay, how about this one?
Still case 1.
Still case 1. Oh, I can't.
it. So we can
case.
keep the.
So how do I get the 4 into a 12?
Multiplied by
By 3.
So I'm getting 9 twelfths minus 1 12. It's 8 twelfths. I'm not done yet because of that rule. I need to reduce. Okay, everyone happy with this one? Sorry, it's not more exciting. I had an undergraduate physics instructor where if you fell asleep in class, you had to come up and take over. So no one fell asleep after. Okay, this one. Someone other than Dan. Which case is this one? This is case 2. Make that 5 look not like a 6. So nothing's in common, and it's not that one is a multiple of the other. So I'm stuck. All I can do is multiply each thing by the other. So now the denominator will be 5 times 4 on both cases, right? It has to be. It's just when I'm multiplying, it's 5 and 4. Okay, if I do something on the bottom, to be fair, I have to do it on the top. Questions on this one?
They haven't done it in a while, but
Oh, yeah.
one.
Okay, which case is this one?
They have something.
They have something in common. So I could multiply 12 and 15, pretend it's case 2, but I'm going to get a big denominator that I'd rather not have. So the thing that was hard to explain well and write well was if we make factor trees of all of these, then what's in common is this 3. Right? The 5 is not in common, the 2s are not in common. So we want to go through our list of factors, and anything that's in common, we cross out one of them. So that's our rule. There was a 3 in both, so we just get rid of one of the 3s. If there were more things in both, we would get rid of the left-hand copy of each pair that happened in both cases. Then our least common multiple, we take everything that's left and multiply it together. So 3 times 2 is 6, times 2 is 12, and 5 is 60. I'm not done yet, I have to find my numerator and stuff, but is everyone okay with this process? We'll do another one if it's halfway over.
And we don't have to.
You don't have to use that method. There were 2 other things to do. One was to just avoid this, multiply the 12 and the 15 by each other. The other was to say, I don't like factor trees and crossing out duplicates. I'm just going to list multiples of 12, 12, 24, 36, and then I'm going to list multiples of 15, 15, 30, 45, until I get to something on both lists. And when you get to 60 on both lists, you can say, there we go, we're done. Okay, how do we get from 12? Need a new color. How do we get from 12 to 60? That was a times 5. How do we get from 15 to 60? 2 would be 30. 4, yeah. There's a trick. Where did I get the 5 from? The 5 is the primes that weren't crossed out on the other number. So this 5 goes over here. Where do I get the 4 from? It's the primes that weren't crossed out on the other number. So 2 times 2 is 4. That goes over here. I shouldn't say not crossed out, not duplicated. So the not duplicated thing goes to the other number. You don't have to actually think. 50 times what is 60? It just tells you. Okay, so 1 times 5 is 5. 2 times 4 is 8. Not gonna have to reduce that because it's a 13. Okay, that was a little confusing. Let's do another one. Should I make the list of multiples since I said it out loud? Is it good to have it on the screen also? Yeah. Or there we go. 60 is on both lists. In this one, I counted 1, 2, 3, 4, 5, and that's where the 5 came from. Or I counted 1, 2, 3, 4, and that's where the 4 came from. On the previous one, then it was that went there, and that went there. Okay. Whoops. If I switch it to 24 on both, it's not much of a problem. Okay, so this is going to be case 3 again. There's something in common, but 2 24s would be 48, so I can't change one into the other. So they both have a 2, I can get rid of one. They both have a 3, I can get rid of one. Everyone okay with the game I'm playing so far? So my LCM will be, there's a 2, a 3, and a 7. The 2 and the 3 I'm not going to include because they're crossed out. And then the 2 and the 2 I'll put on. So what is that? 6 times 7 is 42. Times 2 again will be 84. So 168. Did I do that right? Oops. So then I say, these numbers go there, and that number goes there. Five times 4 is 20. 1 times 7 is 7. as before, if you like listing multiples, you could do that. 42, 84, whatever it would be, 126, and 168, so on with 24. You could actually list your multiples out and just pick the first time there's something on both lists. Okay. Let me actually go back a couple slides. I'm remembering something else. If you like formulas, there's a shortcut formula. The shortcut formula is that your LCM is the product divided by your greatest common divisor. Greatest common, do you use factor or divisor? We use factor, don't we? Factor. So what this is saying is the 12 times 15 was too big. Product, again, is fancy math language for multiply things together. So that was too big. How much is it too big by? That same 3 that we had in common on the two factor trees. Why is that blue? Or on the other slide, once we had our factor trees here, that's right. So 42 times 24 was too big. How much is it too big by? The 2 and the 3. For most people, that shortcut is not actually a shortcut. It's not any more or less work on your calculator to do, let's multiply some things and then divide, than it was on the previous slide to just say, let's multiply a bunch of things. But if you like the shortcut, then there it is. Okay, I just talked too much, so let me review a little bit. When there's something in common, then what's fastest for most people is to make the factor trees. The ones in common, you cross out one of each copy, and then everything else, all the leaves of the trees, you multiply together. And that always works, and for most people, that's fastest, because with your calculator, you can multiply a bunch of little numbers. Some people like using a shortcut formula and have fewer numbers, but it's not really any faster. Your calculator is doing the arithmetic anyway.
Well,
And then some people say, I don't like either of those. I'm just going to list the multiples until I hit something that's on both lists.
so I'm just kind of confused with the 5 and the 4 because you, like on the bottom part, you don't actually times 5. So 1200, oh, so 12 times 5 would be 16.
Yeah.
Oh, okay.
60 divided by.
Right, this is saying 12 times 1, 12 times 2, 12 times 3,
Okay, yeah.
4.
Okay, so that is. All right.
So 3 methods. You only have to learn one. Pick whichever one you like best.
Okay, it is.
It even works if there's more than 2 fractions. So I have 2's on multiple lists. I can get rid of one of them. I have 3's on multiple lists. I can get rid of one of them. So I have 2 2's, skip the crossed out thing, a 3, skip the crossed out thing, and a 5. So 4 times 15 is going to be 60. Question, I haven't done the numerators yet. I'm not done at all. But questions about just to getting the denominators to be efficiently not too big. No question. I'll repeat it anyway. So I made the factor trees for each. But whenever something was on more than one factor tree, I crossed out the second occurrence. And then I multiplied all the non-repeated prime things at the bottom of the tree. Okay, how do we get from 4 to 60?
Multiply by 15.
15. How do we get from 6 to 60? That's 10. And then 4. You could just use like 60 divided by 4 in your calculator to get the 15 if you weren't sure where it came from. You could also say, look at all the trees that aren't that one's tree. And 3 and 5 makes the 15. The 2 and 5 makes the 10. And 4 is there. But it's a little harder to see how that works with more than 2 fractions because you have to look for duplicates. So what do we have? 25, 29, 60. Yes. The LCM product GCF thing isn't going to work with 3 numbers well, but you could just make lists of multiples of 4, 4, 8, 12, so on. You would get to 60 eventually and see it's on all 3 lists if you like that. But that gets to be a longer way of doing things with 3 fractions. Okay. Okay, ready to move on? Enough adding fractions? Your brain is turning into guacamole. this tiny subsection is just a reminder that there's two ways to think about mixed numbers. So I could make everything improper fractions. That's usually the first thing to do whenever I see mixed numbers, and that would work. But if you like thinking about place value, you could do the same kind of thing and say, oh, look, I'm going to take this 3 and make it into a 2 and then a whole. In this case, I don't want my whole to be a 1. I want it to be fourths. And I'm also going to take this 1/2 and make it 2/4. So now my top thing is a number 2, a 4/4, and a 2/4. Oh wait, I don't need to borrow. I'm doing the next problem. Why am I
I'm
making
so
this?
confused.
Yeah.
Don't know what's happening.
Okay. I'm sorry.
just doing something totally-
In this case, I don't need to borrow. I'm jumping ahead to the next problem. So I can take my 2/4, my 1/2, and make it 2/4. 3 minus 2 is 1. 2/4 minus 1/4 is 1/4. And you could do mixed number subtraction just like its place value. But the problem with that is sometimes you need to borrow. Now we'll go to what I was doing badly. So now I say, it's not working. If I try and do 5 minus 3, I get 2, but I can't start with a quarter and subtract away a half, because the half is bigger. So now is when I need to borrow and say, oh, look, let's change that to a 4. And here I get 4/4. And this one is 2/4.
Oh.
So 4 minus 3 is 1. Up top I have 5/4 total. I'm subtracting away 2 of them, so I have 3/4 left.
I'm not getting it.
You know, if you're not getting it, that's fine. Because we can also always do this with improper fractions. And for most people, that's what they like. But for a few people, these things make a lot of sense. Depends on how much carpentry you've done, I believe. So if you like this, then know that you can treat fractions like place values sometimes. And if you don't like this, that's okay.
Wait, can you go?
So what most people will like better is to say, oh, I always hate this mixed number stuff. So I will just make this 7/2 and 9/4. Be done that way. Does that look better for people who were confused a moment ago?
So on the other one where you turned it into 4/4, that's like a whole, right?
Right, I took a
And that's
hole
why
here.
taking 1 away from 5. What about like, you had a different problem, like 5 1/4 minus 3 1/6?
If the 6 was smaller, then that would be to this one where I don't need to borrow. As long as this fraction is smaller than the top fraction, I can just do fraction subtraction over here. So let me finish with the fourth one. So if you didn't like that borrowing business we did, then you could say even this one that had borrowing the first time, we don't need to borrow. We'll just use our improper fractions and everything will be happy. So pick your favorite routine. When you're asked to subtract mixed numbers, either way can work.
Can you go over that again with like maybe a different set of numbers?
Sure. Slowly. Do you want one with borrowing in the fraction one? Okay. So let's have like 9 and a fifth. And we'll take away 2 and a half. So the half is bigger than the fifth. If I just try and treat it like place values, the 9 minus 2 is 7. That's easy, but the fifth minus a half isn't going to work. So if I want to do it this way instead of the improper fraction way, then I'll have to say I need more stuff up in the fraction part here. So let's take this 9 and make it an 8. Take the whole that I'm borrowing and give myself 5 more fifths. So now I have 6 fifths up top instead of 1/5. So I have enough fraction-y stuff that I can do my subtraction. But 6 fifths minus 1/2, well, I need the half to be fifths also, right? So I'm going to change that into something else. Let me write this. So now we're at 8 and 6 fifths minus 2 1/2. So let's make these have a common denominator. And now I can just subtract. 8 minus 2 is 6. 12 minus 5 is 7 of my tenths. Oops, not 41. 36. So my answers are the same because 6 and 7 tenths would also be 67 tenths. Shrink that. Okay. Everyone happy with one or the other? You don't have to do it both ways. I am curious who likes the top method better? That makes more sense. Yeah, who likes the bottom method better? A lot of quiet people. Okay.
I like it because you can kind of see everything laid out.
Okay, onward. By the way, I warned you in the first topic that this thing was sort of a gimmick trick. You're never going to use it in real life. So if there's something that doesn't stick for the final, then this can flee your brain and it's okay. So the mixed number subtraction we just did is that for the second topic. If mixed number subtraction is something that just never really clicks and you're not going into carpentry, then you're probably okay, right? How often does this happen? Okay, here's a great topic. Who has never heard of PEMDAS? Usually there's a couple hands. No, everyone knows PEMDAS? Okay. So there was a couple of things like how to think about division or divisibility rules where I was assuming that your older math teachers didn't teach you right. Here's more ways to think about things. Here's a little extra, right? So this is that kind of topic. If you have been taught PEMDAS correctly, then you are great. There's nothing wrong with PEMDAS. PEMDAS works. Nothing's broken. There you go. But if you are taught PEMDAS badly, through no fault of your own, you are in danger, and let's figure this out and fix anything. Okay? So PEMDAS again, let me make it long. You'll need bigger. Okay. So PEMDAS is this acronym for parentheses, exponents, multiplication, division, addition, and subtraction. Some people have, please excuse my dear Sally in their brain. Somebody should make a better saying than that for that.
I remember it.
You remember it works?
Yeah, I
Okay.
got it.
It's not broken, but anyway. So PEMDAS tells you what order to do things when you see a long, complicated expression. Which of these is correct? Should we say, if I have 8 times 4 divided by 2, then in PEMDAS, the M comes before the D. So let's multiply first and get 8 divided by 4 times 2. So 8 divided by 8, and that's 1. Or should we have 8 divided by 4 times 2? We'll just go left to right. So 8 divided by 4, we do first and get 2. And then 2 times 2 is 4. So let's vote. Who likes the top one? Who likes the bottom one? Most people are not voting. Okay. So the answer is when operations have equal priority, they have to be done left to right. So in this case, all we had left was multiplying and dividing. 8 divided by 4 times 2. So we just go left to right. People who voted for the bottom got it right. Addition and subtraction also have equal priority. Another note about PEMDAS is people sometimes are taught about PEMDAS without thinking about fractions. Fractions are actually just like parentheses in disguise. Anything you write with a fraction, I can also write it with a division symbol. If needed, then I'll use parentheses to keep my numerator and denominator together. So don't do this, but if we really wanted to have PEMDAS correct, it would go PF is one thing, parentheses with fraction marks. Exponents is its second priority. Multiplication and division are the third priority. And addition and subtraction are the last priority. But no one ever writes PF and then E and then MD and then AS in a weird way.
Yeah.
It's awkward. There must be something better than this, and there is. So, do you need to scroll back up?
Yeah.
Okay. Save this. Okay. Okay, so what's better than this? A term is the portion of an expression that's separated from the equal sign only by addition or subtraction. So here's a few of them. I can keep the definition for it. Okay. In this first one, where are my terms? I'm going to keep going, blah, 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 up, and I get to an addition or a subtraction that's not nested inside of parentheses. So that's a break point, and a new term starts. So this one has two terms. How about 37? So I go along, where does my first term stop? Before the 3, because there's a subtraction that's not in the parentheses. Okay, where's the next term? Switch over. There's an addition that's not in the parentheses. So this one has 3 terms. How big is the first term in 38?
4?
The first term, just 311. Where's the next break? Yeah, after the 2. Next break. And one more. Yeah. So 1, 2, 3, 4, 5. So your first goal when you're thinking about these is to get used to seeing where the terms happen. The second thing is that if I actually solve these, which we'll do now, each term is completely separate. I never have to look past the border of that one term.
Do we have to use this method, or can we keep it the same method?
That's not actually a, whoops, that wasn't what I want. A great question, because the other, you can't do PEMDAS without this really. This is just a better way of doing PEMDAS. Okay, so this was our first one. Oops, nope, that's supposed to be a 2 squared. Good thing I checked. And we were saying that it had 2 terms. So each of my terms is totally separate. I can ignore the 8 times 2 squared for now. I just have 4 plus 2 divided by 3. So what do I do first with the 4 plus 2 in parentheses and divided by 3? The parentheses, 4 plus 2 becomes 6. 6 divided by 3 is 2. And then, oops, the plus sign just keeps coming down. On the other term, I have 8 times 2 squared. So what happens first? 2 squared is 4, and then 8 times 4 is 32. When I'm all done, I will have a bunch of stuff with only plus and minus. So 2 plus 32 is 34, and I'm done. Let's go on to the next one. Oops. No. Okay, make sure that there's no exponents not copying right. There is a 2 squared there. Okay. Why am I drawing? So that 22 is supposed to be a 2 squared. Okay, so 1/2 times 4 times 5 minus 3 times 9 minus 1 divided by 2 squared plus 5. So one trick is while I am recopying this, I am going to exaggerate the pluses and minuses that break it into terms and leave extra space around them. That helps my eyes visually say, ah, this is really 3 different problems that'll stick together at the end. So I have my 3 terms. The minus is just going to continue. The plus is just going to continue. Oh, this one's easy. 5 is just 5. So 1/2 times 4 times 5, what do we do first? Yeah, we're going left to right. It's only multiplying and dividing. So 1/2 of 4 is 2. 2 times 5 is 10. How about that middle thing? 3 times 9 minus 1, and then divided by 2 squared. The parentheses first, right? 3 times 8. And I might as well do the exponents too. It's not like a first. So 2 times 2 is 4. So 3 times 8, 24, divided by 4 is going to be 6. Okay? Only multiplying and dividing left, so I go left to right. So 10 minus 6 is 4, plus 5 is 9. So this is still PEMDAS. It's not like we're saying PEMDAS is bad, get rid of PEMDAS. But there's just too much stuff here for PEMDAS to make manageable. You need something beyond PEMDAS to say, how am I going to organize this on the paper? How am I going to organize this in my brain? Ready for the last one? Okay, so, oops. That 3 has a square. Oh. So that's an exponent there. Oops. So again, as I'm recopying this, whenever I get to a plus or a minus that's not in parentheses, I give myself a little space around it to help my eye scan this long string of baloney and say, ah, these are where the terms are. Is it okay if I don't underline the terms? Sometimes that makes it look good. Okay, well, 11 is just 11. I don't have to do anything there. 8 times 2, 16. 14 divided by 7, 2. 19 minus 4 is 15. 15 divided by 3 is 5. 3 times itself is 9. 90 divided by 9 is 10. So 11 plus 16 is 27. Minus 2 is 25. Plus 5, I'm up to 30. Minus 10, I'm down to 20. Questions about this one? Is it looking like something you could do on homework problems? So to review, look at your terrible nightmare thing. Recopy it. Whenever you get to a plus or a minus that's not in parentheses, give yourself a little space, and then just work each term at a time. And no single term can be that bad. Okay, very last concluding thing. You can cancel factors, but you can't cancel terms. This isn't something you will see in math 20 at all, but when you go on to math 60, then if there's terms as part of a fraction, they don't cancel. So hide that in the back of your brain if you're going on to math 60, otherwise don't look at that. When I see you next, we'll start talking about percents. So we have 4 minutes. I have all of your work from Friday. If anyone wants to take it back and fix it up, you can, because I have the scanned copies, which you know, because they're on the website. So if you're ready to have me grade what you did Friday, let me know. If you want this back to work on it with your group a little more, you can. If I don't hear from you by Friday, I will grade everything. Yeah. So, and I'll do attendance while you maybe fuss with that stuff or not, whatever makes you happy. Okay, Abdullah is here. Abelio. I should turn off recording. Okay.